In this video, I'm going to explain how to derive the general equation of finding the area of a polygon inscribed in a circle with radius of 1. So let's start with a triangle, the polygon with the least number of sides. The only information that this diagram gives us is that the radius of the circle is 1. So let's triangulate this triangle into 3 little triangles from its origin, like this. And now, since we know the radius of the circle is 1, so that we know each of these sides has a length of 1, and then we can divide these triangles into congruent little triangles like this. And these are right triangles, which means we can use the trigonometric ratios to find its sides. But we need an angle first. We know that this part, the circle, is 360 degrees. And we know that there are 6 little triangles in this triangle. There are 1, 2, 3, 4, 5, 6. So we divide 360 by 6 to get 60 degrees for this angle. And now, since we know that the hypotenuse of this little triangle is 1, and this angle is 60, we can derive the height and the base with the cosine and sine ratio. So let's start with the height. The height of the triangle will be 1 times the cosine of 60. Now let's do the base. The base will be 2 times, since there are two parts of this base, 2 times sine of 60, since it's the opposite side from that angle. And there we have it. And with these two lengths, we can calculate the area of this triangle with base times height divided by 2, which is the standard equation of a triangle. So the final equation will look something like cosine of 60 times sine of 60. And the 2 is removed because it cancels out with the divide by 2. And since we know that there are 3 triangles like this in this big triangle, we times this by 3. And there you have the area of a triangle. And it works the same for a square. All you have to do is triangulate from the origin like this. And you may notice that the number of triangles that you created is equal to the number of sides in this polygon. And also, if when trying to figure out this angle, you divide it by the number of sides times 2. So based on these 2 examples, we can derive that the general equation of the area of a polygon inscribed in a circle with a radius of 1 is cosine 360 over 2n times sine 360 over 2n and times n representing the number of sides. So let's check that. Here is a hexagon, regular hexagon, inscribed in a circle with a radius of 1. So according to the general equation we derived, if we triangulate it like this, you will have 6 little triangles, and then if you split each little triangle into this, you'll get this triangle. So the cosine of this angle is 360 over 12. So the general equation. So if we use the equation, we can calculate the area by cosine of this angle times the sine of this angle and times 6. And this method makes sense because cosine of this angle is the height, and then sine of this angle is this. And by doing cosine of the data and then the sine of the data, we get the area of this little triangle. And then if we times it by 6, we can figure out the area of this hexagon. So let's get into the questions on the lab. The first question was, how and why is the equation for the area of a circumscribed polygon different? Well, as you may notice, that as you have more sides in a polygon that's inscribed in a circle, you are getting closer and closer to a shape of a circle. But if you have a polygon that's circumscribed around a circle, then it's the opposite. You start with a polygon that's much bigger than a circle, and then its area decreases until it is closer to the area of a circle. And therefore, if you want to derive the equation for that, for the polygon inscribed around the circle, you can still triangulate it from the origin in the same way. The difference would be that instead of having the hypotenuse with a side length of 1, you know that one of your leg has a length of 1 because it is the radius of the circle. And then you also know how to figure out this angle, as explained before. So the equation for the polygon circumscribed around the circle is n times tangent of 360 divided by n, because the tangent value gives you this side, and then since you know the leg is 1, it's 1 times this over 2, and then it will just be 1 times this side. So, and then you times however number of triangles there are in the circle, in the polygon. So now let's get into the second question. What questions, connections, or pattern emerge for you as you work through this problem? Well, we find the answers on the lab that we did, and then as you see, when the polygon is inscribed in a circle, it starts with a small area, and then it gets bigger and bigger until it reaches 3.142, which is very close to the value of pi. And then if you look at the area of a polygon that's circumscribed around the circle, it starts with a bigger area, and then it decreases until it gets to 3.142. So we can say that by calculating the area of polygon inscribed in a circle, and then by adding more and more sides, you can get closer and closer to the value of pi, because the shape of the polygon will look more and more like a circle. Only that if it's circumscribed in a circle, the area increases to get close to approach pi, but if it's circumscribed around the circle, the area decreases to approach pi. And the last question, what problem-solving strategies did you use to build understanding about this problem? So as you see in my explanation that I did, I used a lot of diagram drawings, and I think the diagram really helped to explain this problem, and you can also see why it is so. So that is the strategy I used to solve this problem.